Physics, founding director of the Summer Institute for Statistics Big Data, that's very famous. And the lead of the data management, the statistics core of the UW Alzheimer's Disease Research Center. He obtained a PhD in statistics from UMich while completing the master's degrees in applied math and human genetics. His research lies in the intersection of statistical machine learning, statistical network analysis, and the applications in biology and social science. He is an elected fellow of ASA and IMS and a recipient of the 2022 Leo Brainman Award from the ASA section of statistical learning and data science. So now we welcome our speaker.
Thank you for the kind introduction and for the invitation. I'm excited to be here and to meet with faculty and students here. And today what I want to talk about is relatively recent work for that we've done on inference for function valued parameters. And I'll make this a bit more clear, hopefully, as we go along. And what we're going to use is a version of score test for testing basically functions. This is joint work with my former PhD student, Aaron Hudson, who's now faculty at Fred Hutch Cancer Center, and my colleague, Marco Carone. And really is Aaron's work. So credit goes to him, and the mistakes that I'll make throughout the talk are mine. So here's the problem, that we want to test basically some infinite dimensional or function valued parameter. And you can think of many examples of this. You might want to test the conditional mean. You might want to test the density. So for example, the conditional mean, you want to test whether the conditional mean is 0 or not. Density, you want to test whether density belongs to a particular class of distributions or not. Of course, we can do this in a parametric way. We've done parametric inference. You've all seen sort of parametric inference, the students in classes. So we could characterize that infinite dimensional parameter space by a finite dimensional quantity. So we could do that. And an example of it is that sort of we could think of the regression function as just beta star transpose x. Then the estimation and inference focuses on that beta star. Or we could assume a model for the density. We could assume that sort of our data comes from a normal distribution with a mean and a variance. And then we would be doing inference for these parameters. Now, these are very well defined and standard and sort of understood. Things become more complicated when we have functions, right? So now suppose that our parameter, in this case, the density, the conditional mean or the density is a more general function, but it has some structure. For example, it's a smooth function. So we can't do this without assuming any structure. So we have to put some constraints on it. So usually what we assume is some sort of smoothness or belonging to some function class that is somewhat well understood, but it's defined, it's not defined in a finite dimensional way. So it's infinite dimensional. So this is a parameter that is general. So we do kernel smoothing, for example, for density estimation. And the benefit of this is that we would avoid misspecification of the model. And this has important consequences in terms of bias, inferential bias, especially, for example, in causal inference settings where you don't want to make a mistake because your model is incorrect. And in fact, sort of we have a discussion of a paper that sort of was published in Statistical Science in 2020, where we showed that if you have misspecification of that model, it could lead into biased inference. So there are some approaches out there for inference for function value parameters, but these approaches are either not easy to implement. For example, they require some undersmoothing that is hard to tune, or they're not generally applicable. That sort of, we have some bias correction approaches for some problems, but there's not a general recipe out there for how we could do this. And this is especially, I put this in gray, it's a longer discussion, but this is generally true for local parameters of the distribution. So for example, density is a local parameter, whereas if you think about CDF as easy, or conditional mean becomes a local parameter. I should have said this at the beginning, but please stop me if there are questions at any time. I'm happy to take questions during the talk. Okay, so here's the setup. We have IID observations, Z1 to Zn from some domain Z, and then the parameter of interest maps that domain to the set of real values. So we have a functional that's sort of from Z to R, and this theta star is in a general function class. You have probably seen examples of function classes in classes, and then so the goal is to test for any parameter theta naught, for any null parameter, test whether theta star is theta naught or not. So this is a general test of hypothesis, and the reason that sort of we take it to be any parameter becomes later a bit more obvious because we're interested in also constructing confidence bands for theta star, and this becomes handy when we think about sort of constructing confidence bands for theta star. Now, what do we know about sort of this type of problem? I'll talk a little bit about it, but sort of specifically what we're going to think about is the context where we have theta star as a minimizer of some risk functional. So we have some risk R of theta, and theta star is the minimizer of that risk function. And this is theta star could be we could have settings where theta star is not a minimizer of risk function, but this is a pretty general class that sort of there are many theta stars, many parameters of interest that we could represent them as minimizers of risk functionals. One example that we could consider is where the risk functional is the expected loss, and the loss could be negative log likelihood, for example. So we think about sort of minimizing the expected negative log likelihood, and the parameter that minimizes that becomes the parameter of our interest. So for the example of conditional mean, our theta star is the expected value of y given our covariate x, and sort of our data is x and y, and our theta star could be represented as y minus theta, minimizer of y minus theta, theta of x norm squared. Now, estimation for these subset parameters is well understood. We know that we could get optimal estimates of these, and the optimal estimates usually balance the bias and variance. So this is the bias variance trade-off that we all know about. So we get the variances roughly of the same order as the bias squared. Now this is great for estimation, but then it creates issues for inference because the bias does not vanish. The bias does not go away, and so we can't easily do inference here. And inference becomes difficult because of that bias parameter. Okay, so let's go back to this problem. Consider this testing this parameter theta star, whether it's theta naught or not, and theta star being the risk minimizer, meaning that sort of it's the argument of that R of theta. Then we know that sort of the derivative of this risk minimizer has to be 0 for any. Maybe I'll come back to this a bit later. So we need to estimate this theta star, but let's first think about sort of what are the possible ways that we could test, right? Let's go back to basic statistics. We have a couple different ways of testing. We could do wall tests. So wall test looks at our theta naught and sort of the risk minimizer that we get, theta hat, and looks at the difference between those two. So broadly speaking, wall test is something like theta hat minus theta naught squared, right? So we could do a wall test, and in finite dimensions, we know that sort of this asymptotically converges to a chi-square test. So it's easy because theta hat is normal, and sort of the test statistic becomes chi-squared, and we could do testing. In infinite dimensional settings, when we have now test statistic could be defined as the integral of theta hat minus theta naught over the space that sort of we're considering, then this theta hat might not be asymptotically normal. And then we can't do inference very easily. Another approach that we could take is the likelihood ratio test. So likelihood ratio test is based on that risk minimizer. And we would need to look at the difference of the likelihood. So instead of looking at the difference of theta hat and theta, we would look at the difference of the corresponding likelihoods. Right? So it's Rn theta minus Rn theta hat, theta naught minus Rn theta hat. And that likelihood ratio test, we could again, in finite dimensions, we know that sort of this converges to a chi-square distribution. It has nice properties in terms of efficiency, etc. In infinite dimensional settings, this null distribution of this test might not be available again, and it becomes difficult to carry this test. the last approach that sort of, and it was in the title of the talk, is to use a score test, right? Now, with the score test, what we would look at, we don't care really about sort of, and this is the beauty of a score test, which why it makes it simple and sort of applicable in many settings, including this one. We don't care about the theta hat. All we care about is at the null value, right? So we look at the derivative at theta naught, and if that derivative is 0, then we conclude that sort of we don't reject the null hypothesis. If the derivative is non-zero, we would reject the null hypothesis. That means that sort of if the derivative is non-zero, theta hat is not the same as theta naught, basically, that we're getting. So we would look at that derivative in this case. So in finite dimensions, the score test basically converges to a normal distribution, straightforward testing. Now, if theta naught is not the true risk minimizer, that derivative is non-zero. And the nice thing about sort of score test, as I mentioned, is that sort of we don't need to estimate theta star. And if you remember for these functional parameters, what I said is that we get optimal estimates that balance bias and variance. And the bias that comes from that optimal estimation is coming from the fact that sort of we're using theta star. So maybe if we use the score test framework, because we don't need to obtain a consistent sort of an optimal estimate of theta star, we could get around this whole issue of inference, difficulties with inference. Okay, so here's a recap. Under the null, theta naught minimizes R of theta. Under the alternative, theta naught does not minimize R of theta. So all we need to do is to check whether theta naught minimizes R of theta by examining the derivative at theta naught. That's what we do for score test. And we could easily generalize this to a functional setting if we had a generalized notion of derivative. So if we had a generalized notion of derivative, we could just carry the same recipe that we usually do for score test, basically Rao's test, but in the functional domain. And that's the basic idea. So here's that generalization. It's called the Gâteau derivative. It's a directional derivative. So basically what we do is that we take a direction, h, within our functional space. So that's our theta star. And then we take one direction and we look at our risk function also. So this is a heat map of risk. It's lowest at theta star and it goes up. You see it sort of here. It goes up as we go along that direction h. So if we look at that particular direction, the profile that we get is this, that sort of if we go from one side to another, so we go from, this is high, the risk functional is high, it becomes lowest at theta star, and then it goes up again, right? Along that line, if you think about sort of the heat map along that sort of particular direction h, this is the profile that we get. So this is R of theta star plus C times h, right? For a particular direction h. So for any given direction h, this is a simple parametric family, right? I mean, it's just function of that parameter c. So we could look at a given direction, and the Gâteau derivative is defined as R dot of theta and h as the derivative with respect to c of the R of theta plus ch at that c equals 0, right? So this is how we could define the derivative in any given direction. And for functions, this is also equally defined. Now, the beauty of this is that sort of now we could look at sort of the value of R dot of theta naught h. If that is 0 for all h functions, all possible directions that you could imagine, then you would conclude that theta star is a minimizer of your risk function. On the other hand, if it's non-zero for some functions, then that derivative is not 0. Right? So the problem becomes looking at the value of R dot theta naught h for the null value theta naught to see if that is 0 or not. If it's 0 for all h, then we don't reject the null hypothesis. If it's non-zero for some h's, or sort of I've written them as h prime, then we reject the null hypothesis. Right? So that's really the recipe of the test. That's how we do this testing. So basically, that's the big idea here, and sort of everything else is details. So the idea is that sort of we take it, we can't look at all possible h, so we do a restricted class of h value functions. So what we do is that sort of we look at whether there is an h prime within some large class of script h, such that this quantity is non-zero. So we calculate the Gatour derivatives for different h's within that family, and this becomes what we've called the restricted score test, because it's restricted to that function class of the directions. So that's really it. I mean, if you got this, then the rest of the talk is somewhat redundant. Any question on this general sort of setup, please? So Shojaie derivative could also work, but the Gatour derivative has some nice properties in terms of being able to characterize the distribution of the test easily, and it's sort of used quite a bit in same parametric and non-parametric inference. But I mean, Shojaie derivative is another option for sort of defining derivative in the functional class. Absolutely. I'll get to that. Sort of how do we define sort of a test statistic, because it's over many h's potentially. So I'll get to that. So those are the details that I need to define. I mean, I've given you the big picture idea from sort of 10,000 feet, but I haven't told you exactly how we do this. Hopefully that becomes more clear. Any other question? Okay. So going back to this, the general idea is that sort of if h is not too large, if this is a Donsker class, then the process will be Gaussian, and testing becomes testing whether the mean of a Gaussian process is 0 or not. And this could be. Now, I need to give you some details in order for this to actually work. We need to talk about sort of estimation of the Gatour derivative. How do I estimate this Gatour derivative? We need to think about sort of how to construct this class of functions h, the general idea, so this general idea works. And then how do we define test statistic? Then how do we get the limiting distribution of that test statistic? And finally, the construction of confidence intervals, I'll also talk about it. So that's what I'm going to talk about in the remainder of this talk. So let's think about sort of estimating that Gatour derivative. So it's a directional derivative. And I'll talk about the estimation of Gatour derivative in the context of two examples, because it's easier for the talk to discuss it in the context of examples. And I'll consider two examples. One is non-parametric regression. So we have y equals theta star x plus noise. And so my risk functional is expected value of y minus theta hat, theta of x squared. The other example, a more complicated example, is the partially additive model, where I have the same as before, but now I have another function f star of w, where the w's are nuisance parameters, right? So in this case, I need to estimate the nuisance parameters in order to carry out my test. But it's very similar. The main difference is the additional nuisance. Okay. If there are no nuisance parameters, in general, sort of this is a simple problem. So we could get the Gatour derivative by sort of looking at our empirical risk minimizer. Empirical risk functional. So Rn of theta naught becomes average of our expected our empirical loss, and we could look at the derivative of this. Basically get a plug-in estimate of this. And it turns out that sort of that would be asymptotically linear, meaning that R dot n minus R dot could be written as average of some function plus some remainder terms that are small, little op of n to the minus 1/2. And that average of some function, this is the famous influence function that has been used in same parametric and non-parametric inference going back to, so for example, Bickles. Right. So we could write it as an average, and the fact that it's an average, basically, we could get a central limit theorem, and then sort of everything works. Please. It's actually not a bad idea, but I'll get there. Yeah. So that's a really good question, actually. So the main challenge with basis expansion type approaches, and in fact, there's a paper that I'll mention recently got, so they did for the additive model. They did that for the additive model, is the fact that you would need to do undersmoothing. You would need to sort of somehow figure out the right number of the tail and of how many terms to include. And that's hard to tune. So tuning of that approach becomes difficult. So it's difficult to implement it in practice. But if you were able to figure out sort of where to cut it, that basis expansion, that approach actually would work. I mean, the sieve type inference is something that sort of people have used in practice quite a bit. And it's a really good approach. It's some problems is problem specific. In some problems, it could be done. And in some problems, it's just difficult to tune. So what I'm trying to do is a general recipe that sort of would work for a broad class of problems. And what I'll sort of hopefully argue by the end is that sort of this is something that sort of would work for a general class of problems. But the approach that you mentioned is absolutely valid. The question? So the question was that sort of, if I, instead of thinking about sort of my function f, my function theta, I could think about sort of the simple example of the first example, the non-parametric regression example. So I could represent my theta star with some sort of basis expansion, right? I could think of, I mean, the simplest thing I could do is to do a Taylor expansion of my theta star. It's a function. There's a Taylor expansion for it, right? So I could think of the Taylor expansion, and I could test the parameters of my Taylor expansion instead of testing the function, right? What would I gain by thinking about sort of the Gateau derivative instead, and restricting the Gateau derivative to be in some functional class? You could also restrict the basis expansion to be some number, right? Instead of some number of terms that is including your basis expansion, and test those parameters. And what I gave in the end, in response, was that sort of that's absolutely valid. The challenge is how far do you go in your basis expansion, and that becomes the problem in that case. I mean, it's hard to tune, but otherwise that's a totally valid approach. So this approach also works if the nuisance is not very complicated. But in general, sort of without nuisance or with simple nuisance parameters, we get something that is really simple. The plugin is already asymptotically linear, so we could carry out sort of we could use that plugin estimate. And when the nuisance is more complex, then the plugin might be biased. So that plugin estimator might be biased, and it might behave poorly. The interesting thing is that sort of we could still do asymptotically linear estimation by correcting for that bias, because unlike direct estimation of the parameter, we're thinking about sort of the risk functional. So the bias of that we could adjust, and we could use one-step adjustment, TMLE, sort of et cetera, et cetera. And this is really where the stat goes in. The statistical sort of analysis is bulk of it is here. So I'll try to explain this setting in the context of that partially additive model. So again, going back to the simple case, the non-parametric regression, if you think about sort of any fixed direction h, then it turns out that the Gateau derivative is something that actually makes sense. So it looks at the residual at the null, and then the product of that residual with h of x. And it's if r dot is 0, means that sort of these two are orthogonal to each other. So for any h in our function class, it has to be orthogonal to a residual. And if that's the case, then we would conclude that sort of theta star is equal to theta hat. I'm sorry, theta naught. So we could use the plugin estimator in this case, as I mentioned. So we could use average of yi minus theta naught times h of xi. And sort of that, basically, we could use it directly. And in this case, in fact, actually, the bias is exactly 0. So there's no remainder term. So we get something that is asymptotically linear and unbiased in this simple case. In the partially additive model case, this nuisance function f star makes things more complicated. So it's not as simple, but we could still do something very similar, actually, it turns out, to the simple case of example 1. We could rewrite the nuisance as mu of y given w. W is the additional sort of stuff that we don't care about, minus mu of theta naught given w. So conditioning on w. And then the Gatoux derivative, we could write it in this form, that y minus theta naught, that's the first term that we also had, the residual. But here now we have to adjust for this additional stuff that comes from the nuisance. And then we look at that residual, that adjusted residual, whether it's orthogonal to h minus, again, sort of some term that is the effect of the nuisance. So if we estimate these quantities, mu of y given, mean of y given w, mean of theta naught given w, and then the expected value of h given w, we could carry out the testing in the same way that sort of we were doing it before. So again, we could, yes, of course. Yeah, it is the efficient influence function. Yeah. So the influence function is exactly that. Yeah, sure. For a given h, so we could obtain asymptotically linear, plug in estimator this way, and sort of everything goes through. The challenge in this case really is that we don't need just asymptotic linearity for a given h. We need uniform convergence over the whole class of script h. And that requires some additional assumptions that are sort of a bit technical. I'm happy to talk offline. But basically, we need to be able to consistently estimate the nuisance parameter. So if we could consistently estimate the nuisance function f star, then everything works. Okay. So I talked about sort of estimation of the Gatoux derivative. How do we do testing? So again, we want to determine if theta naught is a risk minimizer. And for that, we want to look at the value of r dot theta naught and see if it's 0 or not. And we do that for h within some restricted class of h script h. And for this class of functions, what our recipe is that sort of we look at an asymptotically linear estimator r dot n. That sort of this is the efficient influence function phi star. And really, we have many h's here in this class, right? I mean, we have the whole class of functions. So we need to, going back to your question, we need to think about sort of an appropriate norm over that class of functions. And once we have a norm, we could just take our test statistic to be norm of r dot. Now, how do we choose h first? Again, sort of we go back and think about sort of first a single h, a single direction h. Turns out for a single direction h, the most powerful test that we can get is the one that maximizes the ratio of the Gatoux derivative over the variance at theta naught. So we basically try to expand this idea, and we take the h because we don't know what h is, what appropriate h is. We have to use a data-driven approach to find the right h. So we take the h to be a smooth function class that contains this sort of maximizer, basically, is sort of a set of maximizers. And the good thing about this and what makes this work is that we can often characterize this maximum analytically. So we could get this sort of form of function h. And then once we have h, please, of course, of h, so I'll give you more details on how we construct h in a couple of slides, actually. Yeah, so I'll give you more examples, but we use, like, for example, an RKHS, a reproducible kernel Hilbert space, and we construct h as a based on the norm of the RKHS. That's like in a nutshell, but I'll get into details of it a little bit more. So our test statistic is norm of that sort of r dot n, and this is some norm, and then we can define many norms on class of functions. There are many choices. In particular, we've looked at two of them. We could take the sup norm, or take the L2 norm. So the sup norm is the supremum over h, the class of functions h of that quantity, and the L2 norm is the average over possible h's. Now, intuitively, when would each one of these two work well? The sup norm works well if there is one or a few sort of function classes and function directions h, where you clearly reject the null hypothesis. Whereas the average works well when you have many of these directions h, that sort of each one of them shows you a little bit of deviation from the average. And sort of when you integrate over them, you get rejection of the null hypothesis. So they capture different alternatives. There's no unit. So perhaps going to your question in terms of multiplicity, there's no uniform norm that sort of gives you always the right power. So it depends on what the alternative is. And that's the same challenge that sort of people have looked at in high dimensional testing. That's sort of the right norm. For example, in high dimensions, you could use something that is based on max, or you could use something that is based on average again. And Tony Kai has a really nice paper that sort of has looked at sort of the powers and properties of this type of test in high dimensions. This is very similar to that. So there's no general recipe, and of course we don't know what the alternative is. So we can't answer that question exactly. However, sort of taking a slightly sort of Bayesian perspective to it, if you had some knowledge about sort of where interesting directions h might be in terms of alternative, the L2 norm might be more effective. So if you had some knowledge of sort of where to look for possible directions h, then you could put more weight into those directions when you're taking the average, and that might become more powerful. But again, sort of usually we don't have that knowledge. Sorry, question. I mean, what I was saying is that in general we don't know, right? So I don't have an answer for that. I mean, in sort of, I think my own sense is that without any knowledge, usually the supreme norm will work better. But so there are situations where, I mean, even in high dimensions when we test, that testing with the average might be better. Especially if you have many directions that each one of them shows you a little bit of deviation from null. And then when you integrate them sort of through the average, you might benefit from the L2 norm. Otherwise, the supreme norm would work better. Yeah. So exactly. So you can't always get that, but so here you're looking at a class of functions that's where you might get it, because you can't get sort of what you just said exactly. Sort of you can't get this exact minimizer. I'm sorry, maximizer, but we could try to estimate the class that sort of contains the maximizer, and that's here the idea exactly. Yeah, of course. So some sort of norm, appropriate norm, again, so the norm is a question. But regardless of the norm, under the null, sort of either of these two would be roughly zero. Otherwise, it would be diverging, going to infinity. And so we need to find a limiting distribution of this. And this limiting distribution is tractable, but might not be closed form. So what we do is that sort of we use a multiply bootstrap for that. And so basically, we have an asymptotically linear estimator, and that's the efficient influence function. We basically estimate these parameters, phi star and theta star, and then we use a multiply bootstrap, basically taking some independent Gaussians and constructing a test that sort of constructing a direction that is based on that multipliers, and then basically if we look at the Rn dot for those sort of multipliers, then conditional on the data, that also converges to the same Gaussian process. So again, there's a lot of details here that I'm not going through but basically we get convergence to the same Gaussian process. So we could approximate the null distribution by looking at norm over this many repeated draws from our multiply bootstrap distribution. And this sort of is under the same sort of type of regulatory assumptions that sort of you expect. Now, going to computation and sort of thinking how we construct this in practice. So in practice, what we've done is that we've taken our S sub k to be some reproducible kernel Hilbert space with a norm J. And then we construct the function class H as functions with bounded RKHS norm. So going back to your question, this is basically how we construct H. And we construct H as all the functions that sort of the norm is less than some gamma. And the gamma is set to maximum, so as an estimate of this maximum. Remember that, so this would give us a maximum power. So we want to construct the direction so that we maximize our power. And that's again, sort of, we need to find the direction, the function class H in a way that sort of gives us the best chance of rejecting null. And this is basically what I had mentioned before, that sort of for a single direction, this maximizes the power. So we get an estimate of this quantity, and we could, the reason that we use an RKHS is that we could use the eigen decomposition to actually do this computation. So that's how we do it in practice. Now, how do we construct confidence bands? Basically by inverting test statistic. Yes. It's this parameter sort of gamma that sort of is critical, right? So the bound on the norm for the RKHS that is critical here. So yes, the choice of the kernel is, I mean, so whether you go with the Gaussian kernel or something else, that's an important choice. But presumably, if you have representation, if you have like a RKHS that sort of represents your class, and that's something again that sort of is not always clear. But if you have an RKHS that represents your class, then and basically what matters is this gamma. That's the truncation factor. What the norm should be, and we get a data-driven choice of gamma that sort of, we don't need to guess it. We could estimate basically. And what we have in the paper showing that sort of for the adaptive version, this also works. Please. So the supremum here is over H's in sort of L2 of 0, right? And that's sort of this functional class that sort of are the class of functions that sort of directions that basically we could get in that space. Yes. 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 I mean, it's not an NP-complete problem. It's actually not, competition is not too bad for most problems, but it is computationally involved. I mean, we're optimizing over, I mean, again, sort of for Gaussian kernels, for example, and I mean, if you define an RKHS based on Gaussian kernels, is actually not bad. But it's yet, so the asymptotic distribution of the test statistic is not tractable. Okay, and so I mentioned at the beginning that the reason that sort of we can consider this general test of the form theta star being theta hat being theta star being theta naught for general theta naught is because we could use it to construct confidence bands. Basically, we invert the test statistic to construct confidence bands that is a set of parameters for which we don't reject the null hypothesis. Same thing that we always do. And in fact, turns out that sort of the minimum and maximum of this set, we don't need to sort of look at all of them. The minimum and maximum could actually be obtained directly by optimizing over this class. So we could optimize over some class of theta functions that sort of get the minimum and maximum, and that gives us a confidence band. So the idea is that basically for every value of x, we look at sort of the minimum and maximum, and so that's the minimum and maximum for this function. So that gives us the band for that particular x. Then we move to the next one, and maybe I'll be able to show you how this works in practice. Looks like the movie is not coming up here. Okay, I had a little bit of a movie showing you sort of how we could get the minimum maximum at each particular point, just going like this. We do it for different points within our domain, and then we basically construct a confidence band by sweeping through those. And this is a valid confidence band. It's a simultaneous band for all functions, functionals of theta star, not just evaluation functionals. And theta cannot. So one thing that sort of I should emphasize here is that we're doing this optimization over some superclass sort of thetas. So this is some smooth functions of theta. Now this is something that, unlike the testing, this is actually something that sort of connects to the undersmoothing stuff. So here theta, we need to this theta to contain our actual theta naught, and this is not guaranteed. So we don't have, this is where we become a little bit hand wavy. No, I didn't talk about bias. I think I understood, and I think that's how I had understood your question. Maybe my answer is not getting at it, but what I'm trying to say is that go back a little bit. That sort of here we have a way of determining the bound on the upper bound on the norm in a data adaptive way. That sort of we get the test with maximal power. Whereas for the basis expansion, that's not clear. Or at least it's not clear to me how you do that. Yeah, I'm happy to talk offline and sort of go into more details on it. But sort of I think that's the critical difference. And in fact, sort of as I mentioned, so there's one paper that sort of recently came out, and sort of from one of my collaborators, that sort of they take an approach like that, and sort of I've had conversation with him as well about this, and that's what they also pointed to. But maybe we could talk offline about this. Yeah, what I was saying is that sort of this, for confidence band, we need this smooth class of functions to contain our true parameter, and that's not guaranteed. That's something that sort of might not have all the time. So the construction of confidence band requires some additional assumptions. So theta cannot be unrestricted, but can be flexible. So we could take a Sobolev class. So this is like somewhat similar to what you were proposing. And we have guaranteed convergence if our theta star is in theta, but it would be challenging for data adaptive theta. So this is something that, again, a little bit hand wavy in our derivation. And the confidence bands that we construct are it's an envelope, so it's conservative. So by default, the coverage might exceed 1 minus alpha. Okay, so quick simulations that sort of here are two examples. One is the non-parametric regression example, the simple example, and there was a paper a couple years ago that sort of looked at this problem, and they developed testing specifically for this problem. So we will compare with that approach, and we'll compare in terms of type 1 error, power, and then coverage of confidence intervals and shape of these confidence intervals. And the approach that sort of this alternative approach was based on debiasing. So that's an approach that would work in this simple case. And we see that in terms of type 1 error, the debiasing-based approach works well as sample size increases. The approaches that we've taken based on either L2 or soup norm also work well sort of as sample size increases, but maybe they have different sort of behavior, especially in terms of power when we look at this. And so the power seems to be, for all of them, gets close to 1, but the soup-based norm test has inflated type 1 error for small sample size, whereas sort of the L2 and the debias-based approach have lower type 1 error for smaller sample size. And sort of that's what we see in this example. And the coverages are pretty good. Sort of we have two versions of this test. One is within the oracle, that theta script theta being the oracle, meaning that sort of we know what the class of functions is that sort of our theta star belongs to. And in that case, sort of we could construct a test, or we could try to do that data adaptively. Again, we don't have theory for the data adaptive version, but it seems that sort of it actually works pretty well in simulations that we've done. And these are some of the examples that we get for confidence bands for different. So that's our function, that's our true function, and the confidence band example that we get with the soup norm with the oracle looks like this, with the L2 norm looks like that, and sort of obviously at the boundaries you have the boundary effect. Debiasing gives pretty tight confidence bands, so it works much better in this problem. But ours, the adaptive versions also get close. So the Supremo with the adaptive version and the L2 with the adaptive version get closer to the debiasing approach in this case. The partially additive model, there's currently no other sort of approach to do it, so we don't compare with anyone. But saying quantities we compare in terms of type 1 error and power, sort of again, sort of type 1 error is controlled as sample size increases, power is increasing, but slower than the simple case. And coverage, we have a conservative coverage for all of them, and the width also goes down as we expect, but again, it's in this case it's wider confidence bands. So here's the examples that you get sort of especially at the boundary. And these are different examples. So the adaptive versions, both of them work actually pretty well without knowing sort of what that theta is, but we just don't have theory for that. Okay, so to summarize it, what we've done is that sort of we wanted to develop a general sort of approach for testing and constructing confidence bands. And the key idea here was to do it based on directional derivatives, testing whether directional derivatives are non-zero or not. We have a manuscript that is on archive, and sort of they've asked us for a revision. We're submitting that revision hopefully soon, and we'll see what happens with it. The point that sort of I think is appealing to me about this approach is that sort of it's a general approach that you could use it for many different problems. For example, what we've done recently is to look at sort of conditional average treatment effect. That sort of this deals with it easily. Sort of non-parametric survival analysis, dose response, and sort of Aaron's working on some of these problems right now. Whereas you could develop testing and sort of, as we saw for the simple non-parametric regression, you could actually do better testing and confidence intervals by specializing the tests for each problem. So you might be able to, for specific problems, you might be able to do better. But this is a general recipe that sort of works if you can't do specific directions. We're looking at applications of this for variable importance, and that's something that I'm interested in more generally, and we're doing it in the context of flexible models. And there are a couple of loose ends that we need to better get a focus on. We need to better figure out sort of what the class of H should be. We're basically assuming that sort of our choice of kernel space represents our function class, but it might not. How does it affect the power? These are things that sort of are still future work. And that's it. Thank you. Yeah, I mean, the type 1 error sort of is controlled for the adaptive version. So we actually show that sort of for the adaptive version, type 1 error is controlled for uniformly. Yeah, because you need to have uniform coverage basically in order to be able, because it's not for any H, right? I mean, we look at the norm. So it's, I mean, we need to have uniform coverage in order for the norm to work. So we actually get uniform convergence, and then sort of from that we show that sort of the norm controls type 1 error. And we don't do it for each H separate. Yeah. Sure, of course. You could take other norms. I mean, there are many norms on a functional space. So within RKHS, we could use the eigen expansion of RK. Yeah. So we use eigen functions of RKHS. So once we have our RKHS, you basically just use your eigen expansion there. Maybe if you could tell me a bit more, because I'm not sure. I'm not sure what my answer is. Can you tell me a bit more? So local asymptotic normality. How do you think it would connect here? Yeah, I'm not sure if I see the exact connection. You're probably right, but I don't know. Yeah. Okay. Thank you.